করার জন্য All right, guys. Good morning, everyone. So I'm gonna be using today just to do problems on refraction, mirrors, and lenses. Okay, that should conclude most of this chapter on optics. The assignment 12 has all the problems on reflection and refraction, so I will be doing a few of those. And then I'll be opening today assignment 13, which has problems on mirrors, and then the last assignment 14, lenses and mirrors. All right, so I believe those ones have a few problems here and there. I might review some of those, so I have to take a look before I publish them, just to make maybe 5 and 5 on each homework. But the assignment 12 has all the problems on refraction, all right? And some of those can be a little bit tricky. So I just wanna go over that. I will start with a prism today, and then I will do a few of the double refractions and the apparent height, okay? So let's go with an example of refraction. So 1.52. Okay. So one example will be when you have a prism like this, equilateral, right? And you have light going parallel to the base, like this. So the idea is to find what's the angle of deflection if the value of n here for glass is 1.52. And here we're on air, so n of air equals to 1. What you need to do is need to remember that when light goes from air to glass, it will refract. And then it will refract even more here. It will refract more. Why? Because if I draw the normal here, right? I have an angle of incidence, and then I have an angle of refraction. But if I draw the normal here, there, right, which is 90 as well, there is a big angle of refraction here. This angle here has to be large. That's the angle X, because the refraction is between this and that. And since you're going from glass to air, right, remember, if you're going from glass or water or whatever to air, then when something is refracted, it goes away from the normal. Okay? The angle of refraction is greater than the angle of incidence. So that's your figure. Remember that these are normals. So we call this N1 and N2. That's 90. And then here also 90 degrees. Right? So here we have 90, and here we also have 90 degrees. And this is 60, 60, and 60. Right? That's what you have. So by geometry, since this is parallel to this, we know this angle is 60, and all is 90, so the angle of incidence was 30 degrees. So I apply Snell's law here. I want to find the angle here, theta. Right? So if I apply Snell's law there, I have 1 sine of 30 equals to 1.52 times sine of theta. So sine theta, this is 1/2, is equal to 1 over 2.04. Sorry, 3.04. Yeah. So I then use my calculator, right? Oh, it's incorrect. That's good. And then I have 0.33 for this angle. So my angle on inside the glass, the angle of refraction inside the glass is 19.2 degrees. So that's your first answer. That's the angle here, right? So if let's do it here only. So this is here, 19.2 degrees. But I want this angle here, I want to call it angle Y, to apply Snell's law here. N glass times sine of Y equals to N of X sine of X. I need to find angle Y using this and using this angle here. So I can zoom in into that picture and I have something like this. This is 19.2. This is the angle Y. And this angle here, I'm going to get it by using the geometry here. So here we have a quadrilateral, 60, 90, 90. So 180 plus 60, 240. 360 minus 240, 120 degrees. Right? So I found the angle. Then I can find Y. Y will be 180 minus 120, 60 minus 19.2. 60 minus 20 is 40. So 39.8 degrees. That's important, right? That's the extra step. So you found this angle. And now I can use it to find X here. To find X, what I will say, I will do 1.52 sine of Y, which is 39.8. Right? That's going to be equals to 1 sine X. Therefore, sine of X is equal to 1.52 times sine of 39.8. And let's see what we get there. So 39.8 sine of that times 1.52, 0.97. So very close to 1. 0.97. So the angle X should be around 88, 89 degrees. Let's see.
Professor, shouldn't it be 40.8? It's 180 minus 60. I mean, sorry, 180 minus 120 minus 19.2.
Did I do the arithmetic wrong? 180 minus 1.
It's just 1.
60 minus 20 is 40. Oh yeah, 40.8. I was subtracting more. 40.8, sorry. So I do it in my head.
Thank you.
40.8. So that's okay. Okay, so then 40.8, 0.65 times 1.52. Okay, so it's even greater here, so 0.99. Right, so almost you are getting close to the critical angle there. So 83 degrees. That's the answer. So the angle of deflection here, as the ray leaves the prism, and as I showed you in the simulation last week, is quite large. It's 83 degrees. All right, that's a lot. Why did I say the critical angle? Because there is a point, if the angle wasn't 40.8, right? If this angle was slightly higher, or greater, sorry, larger, 49, 41, 42 degrees, then there wouldn't be any reflection, it will be here. In fact, let's take a look. We can investigate that. When will this happen? And that's one of the questions that you have to answer in today, in the lab that is due tomorrow, right? The critical angle for glass. How will you find the critical angle here? So you are going from glass to air. So the sine of theta critical will be 1 over 1.52. That's what you will do. And let's take a look. 41.13. So the critical angle is 41.13 degrees, or 0.1 degrees. So that means that approximately 1 degree greater than that, so nothing, right? There wouldn't be any refraction. The light will just go and will stay within the prism. And if it's greater than that, if the angle is greater than the critical angle, then you will have something like reflected rays inside the prism. All right? That's why it's important to realize that depending on the density of the prism, so depending on the refraction index of the prism, you may not see a refracted, right? Because if this is greater or smaller, that also changes, right? It depends on the indices of refraction. All right, so that's one example. Let's do another one that is more complicated now. There's a question about what chapters are gonna be in Thursday exam, which is the last exam of this semester, before the final, of course. I'm thinking 5 to 6 questions, so shorter than the exam that was just due today. The chapters that are gonna be for Thursday exam are the ones, so let me just go to here, modules. All chapter 20, so RLC circuits, all the alternate part that we did last week. Nothing on chapter 21, so don't worry about it. I mean, I might ask one question about that in the final, but not in this exam. And all chapter 22. So chapter 22 and chapter 20. So one question on chapter 20, maybe 2, and then you wanna have one question about mirrors, one question about lenses, one about refraction, and one about something else. So we're making 5 questions there. All right. So that's the idea for Thursday. Thursday exam also has limitations, only 2 hours. All right, 9 to 11. That's it. The reason is because there's also exams after that. There's a final for the lab, which I'm also gonna change the time. I have to send an email about that today. All right, for the second group, not for the first group. All right. So that's how it's gonna be. Chapter 20 and chapter 22 from the book. All right. Anyway, so let's go into this problem here. So there is a problem where they give you a light going through a thick block of glass and you see refraction again. So let's see, you have, so it's 2 centimeters width. All right, so this is 2 centimeters. And light is going like this, and then like this. So first of all, I want to draw my normal here, right? And then I want to draw the ray of light going from air to glass and then to air again. And let's make this larger. We need this to be larger now. So we are going to make this line. It doesn't matter. The only thing that you care here is about the thickness. This is a rectangular block. And what they tell you is that, or what they do is they extend this refracted. And they tell you that the distance here is a distance x. They want you to find the distance between the original ray and the ray that leaves the block. Something that you should realize is that when you go from air to glass and then to air again, these two rays are parallel. Because if you think about it, when you do a Snell's law, and let's put the values here. So theta is 40 degrees. Here is 40. When you go from here and then you get the refracted here, let's call this theta. You get another Snell's law, right? If I draw a normal here, you get a Snell's law between theta and the angle of refraction will be exactly the same angle because you're doing a Snell's law again. So you are refining this angle there. So that's why these lines are parallel. Okay? So that's a property. When you go from one medium to another medium and then back to the original medium, the rays are parallel. But there is a distance, right? Because of the refraction, they go in different paths. They want you to find this. The glass has index of refraction of 1.29 now. So this guy has now that. All right. So it's easy to find theta, right? Let's do that first. Applying Snell's law, one times sine of 40 equals to 1.29 sine theta. Now, remember your calculator has to be in degrees in this chapter, okay? Sine 40 divided by 1.29, I get 0.498. The inverse sine, 29.88. Around 30 degrees, that's why I get. I want to round it to make it easy. So this angle is 30 degrees. All right, good. So since these lines are parallel, I can draw this in here. And because they are parallel lines, what figure is this? This is a rectangle. So here you have a right triangle. So my x here is one of the legs of this right triangle there. So what do I need to do? I have this value of 2. This is 2 centimeters. Right? This 2 happens to be this as well. That's 2. So if I have the angle theta, which is 30, 90, 60, I have 2, I can find this side here. This side here, I can find it. And if I have this side, and I want x, the only thing missing will be this angle here, I'm gonna call it Y. So now it becomes a geometry problem. Let's see what you guys are seeing, if it's clear. Yeah, there it is, right? So I want this X. I have this angle theta already, and I want to find the angle Y. But look at that figure, right? This ray is extended. So this ray is this same line, and then you have the normal. So all this angle, Y plus theta, is how much? 40 degrees, because you have this. This is 40, this is 40. So theta is 30. That means that Y is 10 degrees. So you have this right now. Right? Let's make it more 90 here. There. So you have this is equal to 10 degrees. You want this X value. And then you need this side. But then you have this triangle here. So let's use this first. You have 2 centimeters, the angle theta, and that's the refracted inside the block. This was 30 degrees. This is 2. And I want this side, but this is 60. Right? So you can say that the tangent of 60, sorry, the sine of 60, let's call this D. 2 over D is the sine of 60. So D will be 4 root 3 over 3. That's the value of D. And if I use decimals, because they give me values like that, so 4 raised to 3 square root times 4 divided by 3, 2.31. So this value of D is 2.31 centimeters. So I found this value. This is the value of D here. Yeah. All right. So I use this, and then finally, I will use the triangle here. So I have something like this like that, and then I'm looking at this, right? This is 10 degrees, this is 2.31, and I want X. So what do I use in the triangle? The sine of 10 degrees. The sine of 10 degrees is equal to X over 2.31. And that should be very small. The sine of 10 is very tiny. So sine of 10 times 2.31, 0.4 centimeters. So the answer will be 0.4 centimeters. I would say that 60% of the problem is geometry and trigonometry, right? And this is exactly what you have in the second or third problem in the assignment, with different numbers though, all right? So to recall, the only physics here at the end was finding the angle theta. The rest was using some geometry and some trigonometry. So you have to be comfortable with those tools, all right? So I found theta, and then by using geometry, I know that this is 40, but this is 30, this is 10. I have that. So now I need to find this side to find X. And this side, I can find it on this triangle. Remember that this is a refracted ray. And why do you need to know that? I need this D, by the way, because in one question on that problem, they ask you to find the speed of light inside the glass. And then the time it takes for light to travel inside the glass. Let's answer those two questions. Let's erase this. You want to need that there. So, what's the speed of light in glass? Is the speed of light divided by the end of glass. What's the speed of light? 3 times 10 to the power of 8. What's the end of glass? 1.29. So I will get 2.33 times 10 to the 8. Meters per second. And then they want you to find how long it takes for this light to travel this distance. So how long does the light take to travel inside the block? You have the speed, you have the distance. What do you use? Distance over the speed, right? So let's erase this. And then to find the time, inside the glass or inside the block, you do time. Okay, but the velocity or speed, sorry, is in meters per second. So this has to be 0.0231 meters over 2.33 times 10 to the power of 8. So as you will expect, very, very tiny, really fast. 0.0231 divided by 2.33. So I get this 0.0099 times 10 to a negative 8. If I multiply this by 3, so I get 9.9, 1, 2, 3, times 10 to a negative 11 seconds. So using some of the concepts that we introduced last week, right? This is the definition of index of refraction. The ratio between the speed of light in one medium and another. And the rest was just refraction and Snell's law. All right? So that should help you for, this is problem number 3. All right? Okay. Are there any questions so far about this? Let's do a double refraction now. All right. Let's see. So with a double refraction now, we're going to go and use 3 mediums. All right. Here we have only 2 mediums. We still have 1 refraction, 2 refractions, 3 refractions, but we know that these 2 are parallel. So that was there. But now let's see what happens when you have 3 different mediums. Okay? That's another important application on refraction. All right? Less geometry in this problem that we're going to do, but still important that you guys know what happens when you go, for example, in this case, air, oil, and water. All right? So okay, yeah. Let's just give you here. You have a container. And as you know, due to the different densities, oil doesn't mix with water, and oil goes to the top. You have something like that. And then what you will see is light. This is one of the normals that we're going to use. And then you want to go from air towards oil, and then towards water, like that. So this is air, oil, and here let's put water. Let's say that this angle is 60 degrees. I want to find, by the way, there's another normal here. Parallels, because this is 90 and this is 90. I want to find the angle here, theta, and the angle here, phi. So what are theta and phi? The only information that you need is the refraction indices. For oil, the N of oil, 1.48. And the N of water, as you know, 1.33. So that's important. That's why it's drawn like this. When you go from oil to water, the light bends away from the normal because it went from higher to lower. Not very much, not a big difference, but still enough to make it, so phi will be greater than theta, should be. All right. Okay, so let's find first this angle here. And if you think about it, because these two normals, right, these ones here, are parallel to each other, by alternating interiors, this angle here is also theta, right? Yeah. So we know that by parallel lines. Now we're going to use Snell's law to find theta, and then Snell's law to find phi. So this is a more applicative type of problem. Let's do it here. So 1 times sine of 60 is equal to 1.48 times sine of theta. All right. And then I find theta. Let's put it here. And then arc sine 35.8. So the angle theta is 35.8 degrees. Easy, right? And then I went from oil to water. So now, from oil to water, I have, you are inside oil, equals to now 1. That's the angle. Excellent. So that over that. And now, that times divided by 1.33, 40.6, you see? So phi was not much greater, but still greater, 40.6. That's the only thing that you need to sort of remember, right? So that's double refraction. Are there any questions about that? And let's do now an apparent depth question. So that should be actually easy, right? That's an easy problem there. Okay, just applying Snell's law twice. Okay, the other problem will be an apparent depth. When you guys, as I said last week, right? When you guys go swimming, when you guys go fishing, actually for people here who likes to go fishing, right? You will notice that the position, well, I mean, if you go to the river and it's just very close to the surface, it's probably not a big deal. But if you go to the ocean, right? Or if you are in a very deep part of a lake, right? If you're in a boat, you will see what I'm going to explain right now. You will see the apparent position of a fish that looks closer to you in comparison with the actual depth. All right? What do I mean by that? So another application of refraction, besides prisms or double refraction, is the apparent position of objects. So that's another problem that you should be able to master from this section, all right? The thing is that not much information might be given, not even the angles, like in real life, right? In real life, can you measure angles? Not really, unless you have a protractor with you all the time, right? But using trigonometry, you can always find the angles. So this goes like this, right? So I remember doing this problem when I was a student with a coin, and it was more complicated because it was 2 layers. So at least here is only one. This is the fish here. So here you have the fish that you're gonna get. Now, something that you need to know about light is that the trajectory of light is always, it can be reversed. Meaning that if you're looking at a coin or at anything at the bottom of a pool or a pond, you are looking at the light that that object is emanating towards you. So if you are here, you are the one looking, you're the one who is looking at this object, at that fish. The fish is reflecting light, right? And it's going like this. So I can draw the arrows, not just going towards the fish, but also from the fish towards the person there. That's all right, okay? Light only goes in one way, all right? Which at the end of the day, we use that to explain why light goes inside a black hole, right? Because it goes and follows a trajectory bent by gravity, but that's something else. However, because you are in water, or the fish, sorry, is in water, and you are outside, you don't look at the fish in that position. You look at the fish here. This is a reflected, right? A refracted. This is where you are looking. So you are going to extend, your vision extends like this. until here. And you have an apparent depth, right? Wait a second. Wait a second, okay? All right, sorry about that, guys. So that's the position where you look at the fish. So we call this apparent depth. This is the apparent depth. And this is the actual depth, right? The only information you're given is this distance here, 1.85 meters, and the apparent depth, 1.3 meters. So if you are given this, they ask you to find the actual depth. So you want to find this. So this is what they're asking you. They don't give you anything else. As I told you, they don't give you any angles. All right. So how would you address a problem like that? Right? You have to use all the information given. That's why I do it like this, 90 degrees. You have this, you have that, right? Actually, let me see if they give you at least the, yeah, no, that's it. What you're gonna do is by using geometry or trigonometry, you can find this angle here. And this angle here happens to be what? The angle of incidence, theta I. And if you have the angle of incidence, you know the mediums, you can find the angle of refraction, theta R. If you know theta R, you can find this whole leg, because you have this leg here. So you're kind of going backwards, huh? Right? So let's erase this so you get confused. Again, 1.85. This is 1.85. 1.3. So I want to draw it here. 1.3, 1.85. This call is. So what do you use? There you are. You're using tangent. So theta I is the tangent inverse, right? The arctangent. So let's use a calculator for that. 54.9 degrees. So I found this angle. That's the angle there. So now I want to find this angle here. Let's call this theta r. How? That's the only part where you use your physics, right? Is using a Snell's law. Yeah. So 1 sine of that equals to water, which is what? 1.33 sine of theta. And I need theta r because in all this triangle here that I'm highlighting there, in here, you can find that's x. If you have this and you have this, tangent of theta r will be that divided by that, and that's it. So let's see what I get. So sine, arc sine, 38 degrees. So theta r is 38 degrees. So I found this, I found that, and then in this triangle here, I will do so x times tangent, right? So, oh sorry, I want 1.85 over tangent. 1.85 over tangent. So I take that tangent of this 0.78. So 1.85 over 0.78, 2.37. So the value of x is 2.37 meters. What was the apparent depth? 1.3. So I'm talking about 1 meter difference. It gets greater as these values change, right? Pretty much that's what you have to do. Do you have any questions about this or anything you want me to go over again? Is the trigonometry there clear? This part, that, and well, this is the physics. The only physics that you're doing here is that part. There. The rest is all your triangles and your angles. All right. Can you see a problem like this in an exam? Maybe. All right. But it would be the hardest thing that you could see on an exam. Again, this problem is problem 8. It's the last problem on the web assignment. And it's similar or is a harder version of problem 5, where they give you now another problem like this when somebody is on a boat and is shining a flashlight. And then they give you all the information to find theta 1 and theta 2. I mean, it's actually easy, that one. So that's refraction. Normally, this could be a challenge homework depending on the knowledge that you have on trigonometry. All right. Okay. Let's see. So do you have any question about this? Okay.
Not about that, but I was wondering if you were going to do one with the, where was it? I'm sorry, the light pipe.
The pipe, the one that asks you for the critical angle?
Yeah, maximum.
I can do that one. Yeah, okay, let's do that one. That's the last. So that one is the only problem that asks you for the critical angle, right? So they give you what's the maximum angle theta as you go inside, assuming that the pipe index is 1.34. Yeah, so the idea with that one is that you're gonna have a pipe, and then the light is gonna go inside the pipe, but it's gonna stay there. So it's like the problem of the prism, but light is not gonna be double refracted. Light actually is gonna go in one direction, and then it's gonna stay inside the pipe. It's gonna go like this, and then it's gonna go like this. Yeah. So they want you to find what's the angle theta for that to happen. And I don't think you need that 2 micrometers of information there. You only need, so these are problems that are very interesting because you're probably used, like you had in the exam, the one that was due today, with problems they give you a lot of information. But the problem that we just did, or this problem in particular, they don't give you a lot of information. In fact, they only give you one piece of information that you might not even use, which is the thickness of this light.
So we're just finding the angle of refraction. It's just a one-step problem.
The angle of incidence. You want you to find this. So this is the axis of the pipe, and the light strikes there. That's the angle they're asking you. And then light is gonna go like this. So let's, it's gonna go towards the normal. And then like this. That's what's happening, right? Like that. That's why it says that. It says, assume the light pipe has an index of 1.34. Determine the maximum angle theta for which light incident on one end of the pipe are subject to total internal reflection along the walls of the pipe. These are the walls of the pipe. In other words, you want to find this angle theta, so this hits at the critical angle. I need to draw this. The critical angle is this. This is 1.34. Yeah, and this is 1. How do you find the angle critical? The critical angle, sorry. That's the first step. That's the angle on the wall of the pipe. And don't forget, this is 90 degrees, okay? That's the normal for that angle. Anyway, so let me just see here what's the answer. I want to make sure that is correct. Last semester I did this problem and I got something different. So now let's see. 1 over 1.34, 48.26. So the critical angle is how will you find theta? To find theta, you need to use a Snell's law here. So I'm going to zoom in here, okay, what's going on there. So when the light hits a pipe with angle theta, actually, the normal is this one. I just realized that. This is theta, that's the normal. So light gets refracted. So it should have been like that. That's okay. Yeah, it should have been like this actually. This is the angle of refraction. But here was what we found, right? This is the wall of the pipe. We just found this angle theta critical. 90. How do you find theta r? Right? It's the complement. If you find a complement, you find theta r. And then what do you use? Snell's law. Okay, so 90 minus theta critical is 41.7. So theta r here and I use the Snell's law here to find this. So sine theta that. Let's see. Hmm, 63 degrees. What was the tricky part on this problem is to understand what they were telling you. And again, you don't use the thickness that they give in the problem. 2 micrometers, you don't need that. And they only give you one piece of information, which is the index of refraction. With only one piece of information, look everything you can get. I mean, this is the part where like one simple concept can elaborate a whole problem like this. You only have the index of refraction of the pipe, and you can get all those angles. Of course, the condition here is that on the pipe, on the wall, there's gonna be total internal reflection. So that's when you know that you are using theta critical. There, right? Both. So by knowing that that's theta critical, you get that. But then what you need to see is that the normal for the incident is not like this. The angle of incidence is always respect to the normal. And they give you this angle. So the normal is not always vertical. Huh? It can also be like this. You can have light hitting this like this, going from this medium to this medium. The normal is this. That's the incident angle. That's the normal. Then if you're going from air to the pipe, so this is this should have been like this. All right? Because that's the angle of refraction. So that's important that you realize that. So unfortunately, you already have the answer, right? Unless you have different numbers. But this is a very interesting problem. And I have never asked, but I remember in AP Physics, I put a problem like this for the, the Physics 2 exam that they take for college. And they had to do something like this, where they had to use, I don't think it was a pipe. I think it was like a piece of glass. But that's The only problem when you have to use critical angles in the assignment. And it's an interesting one. I will still suggest you guys to do it and to understand it, especially that geometry part, that part, right? So triangle. So if you were wondering why you were doing all that in geometry, now you know why geometry is important. Is you apply it a lot in these sections in physics. All right. So I think I basically covered all the assignment 12 with this. You should be able to finish it today. All right. What I want to do today after now is I want to go and do some lenses. All right. And show you real images and virtual images and lenses. All right. With that, I think tomorrow we can do a combination of lenses and we are done with all geometric optics. What I'm planning to do tomorrow is a little bit of optical instruments. And that will be the last chapter, I believe, that we will cover, because on Wednesday, I might do a small review for you guys to take the exam on Thursday. All right. What I'm planning to do next week is to go backward a little bit. I most likely will give you Wednesday off, guys, as a study day. All right. Because remember, the final is limited to just the class time. Well, 2 hours again. All right. And it's going to be, I'm thinking 30 questions, multiple choice. So you have a limited window for the final. So it will be a good idea. What I will do on the 12th is I will be available for office hours or Q&As if you guys want to, if you have any questions. All right. But I think it should be fine. Do you guys have any questions or any requests for this chapter? Or anything you want me to go over? Okay, so let's do some biconvex lenses and concave lenses. Let's find magnifications, maybe even a combination, we'll see. Okay. So with a biconvex lens, remember, you have the axis and you have your lens like this. That is a biconvex lens or a convex lens. It has two surfaces and you have a focal point here and here, right? Because of each surface. So let's call this F. And then you have the center of curvature, that was the focal length, and then you can place an object in here and we want to know the image. That's the focal length. So the first ray is like this, and then you have the one that goes to the center. So what I just drew here is the image. So let's characterize this image. The image is real now because it's on the other side of the lens. You can put a screen here and you will see the image there. Right? That's one of the ideas behind the last lab that you're going to do, the lenses lab.
Can you repeat that? Can you repeat that concept just one more time?
What, the fact that
Real?
real?
Yeah. Is it but why it's real?
It's real because now there is not really a virtual or real side or like in the mirror case. It's real because you can project this on a screen. You put a screen there and you will see the image. It's also real because Q is greater than 0. If you use 1 over P, remember, that equation follows, right? the focal length for this type of lenses is greater than 0. And P is greater than 0. So then you get that as positive, right? The image is also inverted. So this is the thing though. If the image is inverted, doesn't mean that the image is virtual. Huh? The image can be inverted and real. And just by looking at it, the image is larger. M equals to minus Q over P. Now, what's the sign of M? Because Q is greater than 0, M will be negative. So it will be positive or a positive with a negative. No? So that's how you characterize an image like that. That's an example. So real images in lenses are different than real images in mirrors. In mirrors, real images had to be on the same side where the object was, right? Because the phenomena is different. In here, we're studying refraction. Light gets refracted. In the mirror case, we were doing reflection. So rays were coming back, were being bounced back. So that's why it's different. All right. The other reason is because in a mirror, you only have one surface. In a lens, you have two surfaces. So you have two focal points. Right? This is also a focal point. That's why you have to be careful. The equation is the same. Let's do can you get a virtual image in a lens? Yes. So let's do it here. So how do you get a virtual image on a lens? For a lens, right? Again, you have something like that. And then you have your lens again here. It can be the same lens as that one. But now the focal point, which is here, now I'm gonna move the object closer. I wanna place the object here, between the focal point and the center of the lens, or the lens itself. This focal point is the same here, so that's F. So what are the rays? Like that. But then you have something going. They are never going to intersect there. You are never going to be able to see the image from over there. But what do? We extend this. And that's your image. This is your object. And this is your image. So let's characterize the image. You cannot put a screen here to see the image. That's tricky. So the image is virtual. The image is also upright. And clearly larger. So Q is less than 0 for this case. If Q is less than 0, then M is positive. Makes sense. M is negative when the image is upright. When the image is inverted. If the image is upright, M is positive. That's a review of what we did last class on lenses. And in some way, similar, not the same, similar to what we did in mirrors. Let's do problems now. All right, typical problems on lenses. And for that, I'm just gonna use the sample problems here. Let's see. Actually, let's use this problem to show you a diverging lens. So this was a convex lens with a concave lens. There are not two cases or three cases. There is just one case with a concave lens. So here. You always get virtual images. A concave lens is drawn like this, right? Concave and concave there. Also, two focal points. That's fine. But you know what happens? When you have an object, wherever you want, the object here, light gets diverged. But it doesn't get diverged randomly. It gets diverged on the same line as the focal point is. Like that. So if this is my focal point, light gets diverged like that. Right? So how do you find the image? You also do this way. That's your image there. That image, again, is on the same side of the object. So it's virtual, upright, but always smaller. That's similar to the convex mirror, right? So do we use these lenses? Yes. You will see tomorrow when we do the optical instruments that there are applications for this. For people who are nearsighted. For nearsighted people, you use lenses that if the object is too far, it creates an image closer to your eye. So then your eye, if you have your eye here, right? That's your eye. It will look at the image exactly on the retina. Yeah. We'll talk about that a little bit next class because we have applications for both, for nearsighted and farsighted people. All right. For a farsighted people that can look at that they can only look at objects. This is a good example actually, because you can have the lens here and the object that is close to you. But remember, it creates an image that is far away. And then there is something called the far point and a near point. And then you can actually look at the image, right? The reason why people wear lenses is because the image is not being formed on the retina. So what the lens does is it creates an image of the object to be able to be projected on the retina. When that happens, you can fix your eyesight, right? But again, that's an application. We'll talk about that, but I think it's good to bring it anyway. Okay.
So if the object is between the lens and the focal point on a concave lens, the image will be larger?
You will still get a virtual image.
But it'll be larger, right?
No, it's smaller. It's always going to be smaller. For a concave lens, right? Or
yes.
For the convex of the concave lens.
Yes.
For the convex lens will be larger. For the concave will always be smaller. And it's easy to prove that. For any concave lens, the focal length is less than 0. Right? P is always greater than 0. Let's just use algebra, okay? 1 over P plus 1 over Q is equal to 1 over F. This is some values. For a lens, this could be minus 15 centimeters, and P can be whatever to 20 centimeters. So look, 1 over 20, 1 over Q minus 1 over 15. If you solve this, Q will be negative something. If Q is negative, the magnification will be minus something over something, right? So it will be positive. If the magnification is positive, then the image is upright. But because Q is negative, it's good. When I was a student, that's how I figured things out. I didn't do the ray tracing. However, ray tracing is important though. You can prove it with ray tracing. But I figure with the algebra, I can get all the properties as well. So if you guys are at some point on the spot where you don't know, just use numbers like I just did. And especially with concave lenses, it works, right? The magnification is an underrated factor in this. Magnifications give you a lot of information. They tell you what type of image is, and sometimes they even tell you if it's real or virtual, because the magnification depends on the sign of Q. If Q is negative, that means that the image is virtual. If Q is positive, hence magnification negative, then the image is real and inverted. So how do you get all this? Practice is the only way, all right? By doing different problems, different situations. That's why when you guys do the lab tomorrow on this, make sure you try and pay attention, because there are like 4 situations that we're gonna do. And each situation has its own caveat, right? Anyway, let's do a problem right now on this. So let's use one of these practice problems here, right? They give you a plant. So a plant is 4.1 centimeters tall and is placed 10.3 centimeters from a convex lens. So it's placed 10.3 centimeters from, so they give you already what type of lens? From a convex lens. The image is virtual and 6.2 centimeters long. Oh, that's a good problem. So if you have a virtual image, .1 centimeters tall. What's the focal length of the lens? All right. Think about it for a second. A plant is 4.1 centimeters tall and is placed 10.3 centimeters from the convex lens. You have a virtual image, 6.1 centimeters tall. Find the focal length. So you need to find the value of Q. One question, is Q positive or negative? That's the only thing you need to know from that problem. Is Q positive or negative in this problem? there. Virtual image means that Q is negative. The other hint is that it's larger than the object. The only scenario where you have images larger than the object is when the object is when the image is virtual and negative, right? It's when the object is too close to the lens. So why do I need that? Height of the image over height of the object is equal to minus Q over P. They both upright. Height of the image over height of the object. What's P? 10.3. So Q will be a negative value when you solve that proportion there. $15.3. So minus 15.3. Makes sense. Is behind the object. I have Q, I have P. So 1 over 10.3 minus 1 over 15.3 is equal to 1 over 8. I also need to know and remember that the focal length will be positive because we're dealing with a convex lens. So if I get a negative focal length, then I did something wrong. But given those numbers, I know that the focal length is exactly positive, equals to 31.5 centimeters. So the focal length by solving that is 31.5 centimeters. Are there any questions about that? So I still think that this is a very easy chapter. Huh? You only have a couple of equations, but there are a few concepts. If you know the concepts and if you practice them, you're gonna be right. The only hard problem that you might get on the exam might be a refraction problem, but not even those ones. I think I covered enough of those today as well. It's all being recorded. What I wanna do now in the last few minutes, so I wanna do the applications tomorrow, is I wanna go over the exam that you guys just submitted. Are there, or is there any question you want me to go over? Remember that next week is the final. Now, you're not gonna get those level of questions in the final, but is there anything you want me to like go over from that exam, a question in particular? I know there is one that a couple of you sent me emails about, but is there another one or any weird answers that you got? What about the solenoid question? Was everybody able to solve that? Where you have to find a number of terms. Laboratory, service, labs. Okay, most of the due dates that you are seeing are probably for labs. Optical ray tracings, RC circuits. The final exam is the 13th, so it's the only thing I have to change here. And by the way, you can take a look at that final if you want. It's a final from last semester. It's not gonna be the same that you're gonna take, all right? So there is a final actually, guys, that you can take a look. So it's already published there. And then there's no quiz, and test free is on the 6th. let's erase this because that's irrelevant. And that's on the 6. Yeah, there's a lot of due dates for labs because there's 3 labs still left to go. Okay, so let me at least solve you the one in the with the capacitor one. Oh, where is the exam? Here. They gave you a capacitor and the only information was the distance between the plates and the voltage, right? So what is the assignments? This number 2. There it is. So they give you a particle going with 2 times 10 to the 6 meters per second, 3,000 minus 3,000 volts, 12 millimeters. What's the magnitude and direction of the magnetic field, right? I made a change on that question. So what is the magnitude and direction of the magnetic field on that? All right. So that's 3,000 minus 3,000. Volts. All right. The electric field is going like that. So then the magnetic, there is a positive charge, right? The electric force goes like this as well. Is electric field. So then if you don't want any deflection, the magnetic force has to go and be the same magnitude. So you have to solve this. QVP sine of 90, because if you want that force to be like that, so the magnetic field had to be into the page. QVB equals to QE, cancels, you have velocity, but one question, the electric field. How do you guys compute the electric field? Anybody? It doesn't matter if it's wrong. Did anybody? How do you guys compute the electric field? Delta V over delta X. Delta V is how much? 3,000 minus 3,000, 6,000. Over 12 millimeters. 5 times 10 to the 5. .25, right? Yep. B is 0.25 Teslas. That was the answer for our question. For 1 and 3, so where is this 3? Okay. All right, so problem 3. Problem 1 actually, let's do problem 1. I'm not gonna give the values, but I wanna just show you what you have to do. For problem 1, there was only two relevant forces. You had current, and then you had a loop. Think about it, right? You have like this, and like this. This is the same length. And on the same end, like if you were confused, you could just find the magnetic field, and then the force will be mu naught I1, I2 over 2 pi, and then this will be just like the center, right? The same distance d for both. And the length will be, right, the same length. All right? The current is going down or going up. It doesn't matter. Because if you have the field on this is going into the page. So this is going like this. Into the page. So here is into the page, into the page. Look. A force going like this, but this goes what? Like that. These two forces cancel with each other. That's why you have to figure it out. So just by showing this and that they cancel, the only relevant forces are this one. Why they are relevant here and here? This goes like this goes like that, this goes away. This goes like this goes like that, this goes towards. But they are not the same magnitude. Why? Because this was 7.5 centimeters and all this was 17.5 centimeters. So for these two, the distance was the same. For these two, it's not. For this one, for this force will be mu naught I1, I2 over 2 pi times 7.5. So it's going to be 1 times the length, which was 30 centimeters. And for this was mu naught I1, I2 over 2 pi. The distance will be now how much? 17.5. So D2 times the same length. L was the same, but not D1, D2. This created the difference. So what's the overall direction? The loop is moving away from the current, from the wire. This was the only hard problem, I think, not even, right? Because you had to, if you figure this out, you could just do the subtraction, and that's a net force. All right? For the question 3, they gave you a loop at some angle. It's a circular loop. It doesn't look circular because it's at some angle. And the field was going through at some angle theta. And I did say that if that happens, you just have to break the flux, right? Yeah, they gave you this as well. You have to break into it. So if this was B, you wanted to get B cosine theta. Now, B was decreasing. So the flux was decreasing. That's what you have to do to find the EMF. But remember, this was B cosine theta times the area. The area was constant. This changed because of the B. B was decreasing from 1.5 to 0.5. In any way, so the V that is causing the flux is going like this. The parallel one, this one here, there is also one going like this. It's irrelevant, this one here. So the flux going like this is decreasing. So the induced current, if you have an EMF, the induced current is E over R, and I gave you R, has to create a field going also like that to make up for the decreasing. So, right? So it has to go like this. By going like this, the current will create a field going on that direction. So that was the direction of the current. You can say counterclockwise. All right. The calculations, I think they were not that difficult for that. Then the AC generator was applying the equation MVAW and then evaluating there. Are there any questions? I will try to have this graded by the end of tomorrow. I don't think I will have it graded by tomorrow because I have to take a look. But I think it was an interesting exam. It had a lot of things in there that we covered. All right, guys, so I'm finishing the recording now. If you have